wider experiments like Zeus and B Factory at KK and KTE. And then there I was, and I still am an instrumentalist. So I worked on some detector technologies, and then around 2007, I changed my subject to experimental cosmology. Since then, I've been pursuing CMB mode polarization to test cosmic inflation. And I worked on Quiet, and Polar Bear, Simon's Array, Simon's Observatory in Chile. And then at the same time, I proposed this Lightbird satellite, and then JAXA adopted that. So we hope to launch that in 2030s. So, and then, then during that, I've been involved in superconducting detector development. And then recently, I also involved in quantum metrology. And so these are sort of my background. And then at the same time, I always like to work with some theorists and phenomenologists to propose some new methodology in fundamental physics. So probably my background is a bit different from yours, but it's amazing that we are getting together for the common science here. So then I jumped into CMB polarization with three reasons. One, because we could observe quantum fluctuations of space-time itself. So fascinating. And then number two, we could explore grand unified theory scale physics, which is, of course, a dream of the particle physics. And number three is we have fantastic technology matching with high energy physics and the CMB observations. These are the reasons why I jumped in. And then today I'm going to say a few words on cosmology and astronomy from future CMB observations with Simon's Observatory and Lightbird, and mainly focusing on Simon's Observatory because, as Thomas said, I started this visiting professor position at NCU for 3 years, and then my task here is to launch the activities for Simon's Observatory. So then today outline is after giving some introduction to cosmic inflation and CMB polarization, I'm going to explain Simon's Observatory, mainly science. And then at the end, I briefly touch on Lightbird. So mainly Simon's Observatory, that's my plan today. But first introduction, and then obviously our journey started in 1965 when this cosmic microwave background was discovered by Penzias and Wilson, who got Nobel Prize in 1978. And then current understanding is that this is sort of a remnant from the period when the hot dense plasma turned into the transparent this hydrogen atoms as shown here. And so that's sometimes we call it a recombination. And then, so this is now the direct evidence for hot Big Bang. So before that, we had some arguments between Big Bang and steady state universe theories and stuff like that. So this was the turning point. And then in 1990s, the Kobe satellite gave us a proof of black body radiation beautifully. And at the same time, they also observed the CMB temperature and isotropy for the first time. And that was the indication of cosmic inflation. So that was another breakthrough. And then and Pendia, Mother and Smoot got a Nobel Prize in 2006. After that, NASA launched the WMAP, and the ESA launched the Planck. And on ground, there are very massive telescopes here, ACT in Chile and the SPT at the pole. And then now today we are observing a very nice temperature and isotropy spectra. And then that is the base of our precision cosmology today. And this was the sort of really the main weapon to establish the so-called lambda CDM, our standard concordance cosmology today. Now, what's next? And then the CMB community is really chasing this CMB polarization. And that's a new frontier because the biggest reason is that gives us a chance to test cosmic inflation and hence quantum gravity behind that with polarization of cosmic microwave background. So that's why we think the polarization is the frontier. And then what we expect is that during the inflation, this primordial gravitational waves were generated, and then that had imprinted this specific curve pattern in the CMB polarization map called B mode as like fingerprints of inflation. And then this is by far the most sensitive probe of the primordial gravitational waves today. And this B mode signal is proportional to the inflation potential V, and hence the tensor to scalar ratio, important cosmology parameter that I'm going to introduce in the next. So because of this, people are really fascinated about this possibility. We're chasing that. Now, physics of cosmic inflation, just in one page, is the following. Cosmic inflation is the accelerating expansion before the hot Big Bang proposed in early 1980s. And with known particles and radiation, we cannot create this accelerating expansion. So we need something new. And then usually we introduce this new scalar field phi called inflaton with potential V as a source of acceleration. If you know particle physics, this really looks like Higgs particle, which was discovered about 10 years ago. So, and then, more than 10 years ago now, I guess. And then, and a bit more details. Now, in case of the simplest class of models called single field slow roll inflation, simplicity is always the guiding principle or guideline for the particle physics. We hope to find that theory with, a small number of parameters as much as possible. So, and with that spirit, there are two important relations. One is this relation between the potential and this tensor to scalar ratio parameter, R, and then this is the key parameter we are chasing. And then it happens to be that this relation has and introduces this ground unification scale. So this, we are talking about very high energy physics. So that's why particle physicists are also fascinated about this. And the second is this R relation with this N and delta phi, where N is E-fold of the inflation expansion. And then delta phi is a characteristic scale of inflaton field traveling during the inflation. So, and then because of this, measurement with this tensor to scale ratio down to 0.01 or so would provide fairly definitive statement about the validity of the most important class of inflationary models, which is the single field slow roll models with phi, delta phi exceeding the Planck scale. So in particle physics, so in most fundamental theory, it's very important to know whether there's any parameter exceeding the Planck scale or not. That's really one of the keys to understand the ultimate theory. So, so this measurement will be probably the first time we can really address that sort of high energy quantum gravity physics. So that's why particle physicists are fascinated about that. And then we think this B mode is a smoking gun signal of primordial gravitational waves. So inflation creates actually scalar and tensor perturbations. And then since we introduced scalar particle, and then that itself has quantum fluctuations. If you introduce some new particle, that should have a quantum fluctuation, and that creates this scalar perturbations. And then that's called the E-mode pattern or parity even pattern as shown here. Whereas the quantum fluctuation of the metric itself or space-time itself could produce this tensor perturbation, and that's the primordial gravitational waves, which has a quantum origin. So, and that's the tensor mode. And actually that can create both B mode and E mode. Important point is that this S never creates this B mode. So that's why this this B mode, discovery of B mode is the clear indication of primordial gravitational waves with quantum origin. E mode should have some, this is basically a mixture, but since this S fluctuation is larger, it's really hard to constrain the tensor to scale ratio from this E mode observations, which Planck did, but to some extent. And if we really detect this evidence for inflation and primordial gravitational waves, it's a huge discovery impact. And because it's direct evidence for inflation, and it gives us knowledge on the inflation energy scale, and it's going to be the first evidence, arguably, for quantum fluctuation of space-time. And it's not trivial at all if space-time itself has quantum fluctuation. But we do, naively, we think quantum theory rules also space-time. So that's actually a big assumption, but that's what we're gonna test. And then because of that will even give us insight on quantum gravity, including string theory. Because of that, if you look at, for instance, this report of the task force on cosmic microwave background research, so-called Weiss Committee report. Weiss got a Nobel Prize. He's one of the founders of LIGO. And then, so it states the following: detecting primordial gravitational waves would be one of the most significant scientific discoveries of all time. So, and then if you think about this B-mode power spectra, within the standard cosmology, we have a firm prediction. If R is 0.01, you should expect this two-bump structure. This bump around L of 80 corresponds to the fluctuation at the time of recombination, and the bump at the lower L corresponds to the bump created during the reionization period. And then you see this another structure here, and I'm going to explain that. And then, well, also we have this so-called foreground component, which we need to remove from background. And the foreground background separation is one of the very important experimental challenges today. But let me explain this part, which is called the lensing B mode. That's a secondary B mode by weak lensing. Even if you have just E mode, because of this lensing, your image is distorted, so that original parity even pattern is distorted, so that you can create the this sort of curve-like structure, which is called the lensing B mode. And then that has a peak around the larger L or smaller scale. So if you look at this power spectra, basically you can distinguish between two. Now, and then a bit history of CMB B mode search. I jumped in to this business in 2008 or so, and then I'm proud of the fact that we really first touched on this part in 2014 by the Polar collaboration, which I was involved in. And that was March 2014. And a week after, there was a famous BICEP result came out. They claimed discovery of the primordial gravitational waves. And it really was a top news of the biggest Japanese paper, for instance, Yomiuri newspaper. But turns out that that was due to the dust polarization. They just rely on a single frequency measurement. So with the more careful um, analysis with Planck data, situation changed. And then this was the situation in 2015. And then other measurements, SPT pole and ACT pole came in, and we started really touching on B mode, although this is still, not the primordial, but the lensing B mode. But this itself also gives us useful pieces of information about cosmology. And then we have some more measurement, and then today we have this sort of polarization B mode power spectra. We haven't really seen this primordial B mode, and I also show this E mode. E mode has much larger, power, so it's pretty much well measured by now. And then this part is, as I told you, lensing B mode. And then with this observations, the current bound on R is 0.032 at 95% confidence level. This is mainly coming from bicep 2, Keck, and Planck. And then this is already very interesting because with this, we ruled out the simplest inflationary model, so-called the chaotic inflationary model. So this is already useful for testing some model. So somehow in the history of particle physics, almost always the simplest model won, like conventional star model or Higgs model. So, but in this case, the simplest model, chaotic inflation, the simplest version of chaotic inflation didn't work. So it was ruled out. So that's already very intriguing. Now, because of this big fish, there are a lot of projects chasing this. Polar Bear now upgraded to Simon's array, and then ACT turned to ACTPole and then advanced ACTPole. And then there's a small aperture telescope named CLASS in Atacama. So these three are at Atacama, Chile, and the ACT and the Polar Bear Simon's array merged to Simon's Observatory, which I'm going to tell you today. And then in South Pole, SPT pole, is upgraded to the SPT 3G, and then the South Pole Observatory is coming on, and then people got together to propose CMB stage 4, S4 for 2030s. And unfortunately, recently, the NSF in US decided not to use there's a South Pole for CMBS4. So now CMBS4 is focusing on the measurements in Chile. So it's most likely going to be the successor of Simon's Observatory. And then there are several other projects in other places, Canary Islands, Quixote, Groundbird Strip, and in Argentina, Cubic, and in Tibet, Ali CPT. They are basically, some of them are taking data already. And then in space, this Lightbird is what JAXA is leading, and somehow balloon part is missing. I don't know why. I lost it. But balloon, there are some flights, Spider, and Spider is it took some nice data, and EVEX, and also Piper. So that's more or less situation. But now let me focus on Simon's Observatory. What is Simon's Observatory? It's a powerful new experimental cosmology facility comprising a set of millimeter wavelength telescopes located at high altitude in the Atacama Desert of northern Chile, roughly 1 hour from the town of San Pedro de Atacama. And formed through support from the Simons Foundation. And then we are really, really lucky that the Simons Foundation gave us pretty good support. That's also important because of the instability of the U.S. government these days. This project is mainly supported by this private foundation, so it's to some extent safe from that instability. And then there are a lot of institutions. In my case, currently I work for Simons Observatory as a member at KK in Japan. And telescopes, we have two different kinds of telescope. One is this small aperture telescopes. We have three small aperture telescopes, which started taking data in 2024. And we plan to add this should be three more, will be deployed, and one from Japan and two from UK in about a year. And then that's focusing on this primordial gravitational waves. Another is a large aperture telescope, LAT, which is in commissioning right now. We got a first light recently. And these are photos I took in December last year. And these are so there are Pathfinder experiments that led the way to the Simons Observatory, including ACT and the Simons Array Polar Bear, which I worked on, and the class I mentioned, and the Atacama B mode search. So these telescopes are based on the decades of the experience of this previous projects. Science at Simons Observatory, as I told you already, SATs are focusing on early universe primordial V mode, whereas LAT covers the pretty large areas, early universe, relic particles, neutrino mass, galaxy evolution, blazars, galactic science, even planet 9, and transient sources. So it's a 6-meter aperture. So this is the scanning plan strategy. The left side shows the small aperture survey, which is going to cover 10% of the sky with less foreground region. And then the large aperture telescope, LAT, will really cover the wide range. In this case, we assume 40% of the entire sky. And here, some important numbers. So we're going to cover 6 frequencies between 27 to 280. And with these beam size. And as you can see, at 280 for LAT, this beam size is almost 1 arc minute. And the noise level is really small. And then because of the fact that we're going to we deployed really lots of TS barometers. I don't touch on the instrument today, but if you're interested in that, I'm happy to explain more. But this great sensitivity is mainly coming from the fact that we put really large focal plane with lots of sensitive TS superconducting detectors. And then how many meters? This one is about 40 centimeters, and then this one is about 6 meters. And I was asked, I guess a couple of weeks ago, the field of view for LAT is 7.8 degrees. It's really, really large. So we hope to get this very impressive the power spectra at the end of the day, TT and EE and BB. And then here for comparison, we also plot the Planck and the BICEP 2Keck and Lightbird future mission. And then just the blue points are for Simons Observatory. You can see, for instance, for high L, you see a very big extension from Planck. So, so for SAT science, the forecast on our measurements, it's with SO nominal, we or get this 0.003 1 sigma error, it's almost the order of magnitude improvement from the current limit. And then here it shows the some study results of the foreground removal. Really, the name one of the name of the games is the foreground removal. So the background and foreground must be separated. As an experimentalist, of course, we're also working hard on the systematic error mitigation and stuff like that. I don't have time to go into detail on that. But then here, this current plan, this is a plane in R versus N sub S, another cosmology parameter for the spectral tilt. And then, as you can see, we expect to have some order of magnitude improvement. And then, as a reference here, I show one model called the Stravinsky inflation, which is currently, to me, the simplest model. And then, hence, it's really a good model. And then, but in between this line and the current limit, there are some other models predicting larger value of R. So you have a good chance of discovery. So that's SAT science. And coming to LAT, actually that's a main topic today to me.
Can I ask a question about the survey area? So I thought the LAT area looked larger than
yes.
But then I thought SAT need to go to larger scale. So I was wondering why SAT area is smaller.
Because 10% of sky is really sufficient to cover L down to like a 30 or so.
But then if you want to go, reionization, then
reionization is impossible on ground. So that's a job of like a satellite mission because of the atmospheric fluctuations. It's really hard to get down to reionization bound on ground. So the strategy on ground is really somehow to touch on this tiny difference between the lensing B mode and the primordial recombination bound. So that's a strategy.
I'm not an expert, but then I have a naive idea for SAT, the larger area is important.
Yes, so the larger area important, yes, but it's like 10%. This is the optimum.
Okay.
If you do like in Chile, you can in theory cover like 70% of the sky, but and actually that's what CLASS, another project, is doing, but they are still suffering from all the experimental issues and then atmospheric fluctuations. So you really need to go to space. That's my thing. Touch on the reionization bump. Yeah. And then the Simons Observatory has this 10-year plan. And then the first round of construction has ended. Now we're entering this advanced Simons Observatory project, putting more receivers. And then we'll have, so with the current configuration, we plan to have 4-year observation. And then during that time, we prepare more receivers. And then and around 2028 or so, we'll have this full configuration observations. So this is the current plan of SOLAT observations. And you can see this is science goals from SOLAT, enhanced SOLAT surveys. And then just briefly, let me go through that. So from primordial to really transient or even solar system science. So it's really from the last scattering to the solar system. And then, for instance, this is a primordial cosmology part in Southwest, scalar tilt. With E mode, you can have the current error. So this is really, I'm personally really interested in this one because together with R and LSS, you can really narrow down the possible inflationary models. And also, we expecting to improve by factor 5 the non-Gaussianity observations. And so this is inflation science, and this relativistic species in sub F effective, the improvement factor is also a huge factor 4 or so. And then this is useful to search for or constrain all the possible new physics particles with mass below 1 electron volt or so. For instance, you can try to search for gravitino and stuff like that. And then we can also constrain better the neutrino masses with a combination of other galaxy observations. Here, as you can see, factor 3 or more. And let me move on. And also we can constrain better the reionization history, and then we can have much more, I mean, larger number of clusters and AGN. If you look at this, you can see factor almost, let's see, factor 10 for cluster catalog and almost factor 50 for AGN catalog. And for galaxy science, you also have lots of improvements expected. And these are basically coming from the fact that you can really cover very broad sky with fairly good angular resolution and with 6 frequencies. So let me just, well, I probably don't have much time to, or if you're interested in this primordial part, you can ask me any question, but let me come to here, for instance. So this shows the nice overlap between Simon's Observatory LAT and DESI, Rubin, Euclid, and DS. So the detailed analysis of the detection of photons due to gravitational lensing from large-scale structures and the scattering of photons from ionized gas in galaxies. So they offer exquisite tests of structure formation models and allow constraints on the physical parameters governing these processes. So particularly via cross-correlation measurements. So really one of the true powers of SO lab is this cross-correlation, where you can bring some new ideas. And if you look at our recent paper that describes some cross correlations with, of course, these DESI, Rubin, Euclid, stuff like that, even also with Spherex or even more other X-ray data and infrared data. So there, I believe you can introduce some of your original ideas, proposing some new cross correlation studies, and that's also important for our dark energy studies. So of course, dark energy is one of the most important topics in cosmology today. And then one important thing about our business here is with that scattering nature and then the SZ information and stuff, you can extend the Z range to the higher region, which is not accessible in the optical surveys. So that's one of the real stretch coming from this millimeter large aperture telescopes. So above Z greater than 1, you can get a lot of information from this SOLAT. So, and then, this one, let me see. Well, this one is also that sort of example. These are stacked images of ionized gas density around galaxies measured via the kinetic synapse observation effects. So all these studies become possible. So it's really where the all the astrophysicists and astronomers can also get in and enjoy the data analysis. And then this one, let's see, yeah, uh, and time variable blazars and dusty galaxies. We can have this daily. We have a pipeline for this transient. Uh, Transient, the objects. So that will give us, for instance, some alert or some sort of a precursor observations. Say, for example, to ALMA, and then as you can see, this 5 sigma source sensitivity with a much future source finder is about 2 millijansky, and then so that's for AGN. So as I told you already, like you expect to have factor 50 more objects, and then it's really opening up a lot of possibilities. And then this is a table of the sensitivity to point sources. So and these 6 frequencies are ready to be used. And then this is the expected number of sources as there's a function of cutoff and signal, SN ratio. So here in Taiwan, I'm a small aperture telescope guy. I'm not an expert of large aperture telescope science, but since both data are available, if we join, and my plan is to myself will be focusing on primordial stochastic gravitational waves, and also expansion rate of our universe. Hubble. And then, but as I told you, there are various cosmology astronomy with SOLAT, and then we expect to have many publications with initial data sets in next 2 years or so. And then, of course, important remarks are all the proposals here shall obtain SO collaboration's approval if Taiwan joins. So currently, please not take this for granted. So because of that, do not spread the wrong message that ISO data are already guaranteed to be accessible. So please keep that in mind. But I'll make my best effort so that this is good for Taiwanese science, and then more people become happy. So that's what I'm gonna try here. And I just spend almost all of my time, so just a couple of minutes about Lightbird. Lightbird is a JAXA-led mission, and then as Tomo said, of course, one of the holy goals is to cover the entire sky. So then hope to get this sort of B mode fluctuations. And then skipping some, I'm happy to explain the current status and stuff, but let me focus on science. And then one interesting thing is that with Lightbird, first of all, it's going to have a factor 5 improvement or so compared with Samos Observatory on R, and also it touches on the reionization bump. So this is an interesting model. This is just an example model with some additional new particle. And then that alters the power spectrum from the standard prediction. And then in this particular case, you expect some enhancement if you take this parameter set. So that's never be observed on ground. So that's one of the very important points of having a space telescope at the same time. And then, once we have observations with Lightbird, and then, for instance, if we do see some things like this might also have correlated enhancement in other gravitational wave observatories. This is a paper from April and others. And then, so the point is, if you just take the standard cosmology case, the sensitivity of this SKA LISA Einstein telescope, not enough to really touch on the R of like a 0.01 or so. But in case we have some additional things like this, this model's case, you might see some enhancement and you might see some correlated signal. So this is why I'm saying it's essentially important to have this all the sets so that we have this gravitational wave landscape. And then it's really the measurement decides what we really have. So this, it's not necessarily true that this current standard is true. So it's really important to have these all measurements. So that's a sort of an important point. So let me stop here. The take-home messages are CMB mode is the most sensitive probe for primordial gravitational waves. It's a crucial part of our pursuit of gravitational wave landscape with other probes. And Simon's Observatory has started taking data and will lead the B-mode search in the next 10 years or so before Lightbird is launched, before CMBS4 turns on. So SO has reached scientific objectives, although I started from this emphasizing primordial B-mode. Actually, SO's strength is the fact that it really covers a lot of scientific topics in cosmology and astrophysics, astronomy. So, and then we expect to have really nice sort of a correlation data analysis. So, SO has reached scientific objectives from inflation to the solar system. Although I didn't have time to explain the solar system, Planet 9, stuff like that, but you can read our paper. And then, so it can make, I think it can make excellent contributions to Taiwanese and Asian science. Okay, that's all. Thank you.
Thank you very much for interesting talk. Questions, comments?
So what's the current situation of Lightbird?
Oh, no, Lightbird, yeah, okay. So we are now entering this, we are in this so-called reformation phase. We had a baseline design until 2024, but the JAXA decided that we should simplify the design. And then that's an ongoing activity. And then some, and then also it's written. And also we need to come up with a new procurement management model, who does what. And then this was triggered by KEK's decision not to provide the focal plane detector system, unfortunately. So the new management wants to focus more on the accelerator science. And then, so, but recently we are having some progress. So we will soon, I hope I will make some announcements soon about the new, management plan. And then basically we are planning to keep our science unchanged, but simplifying the design. And then, it's really recently not easy in this current world to estimate total cost. And, you know, in case of Japan in particular, yen is so weak these days. And also because of the war in Ukraine, the things getting higher and higher. And also another thing is inflation, not cosmic inflation. Just, and if you look at the price in US, it's getting higher and higher. And then if you look at, for example, the costly model of NASA, they have some standard inflation rate. And there is some guideline. But the current inflation rate, in particular in the last few years, was far above that. So in that case, you know, it's a challenge these days to have a reliable cost estimation, and yeah, so that's what we are facing right now. But that's not only LightBird. Other projects are also facing some issues, and you heard about some news from US, for instance, for NASA cutting budget hard, yeah, stuff. So it's the world is now becoming unstable, unfortunately. But we shall do whatever. I mean, the best we can do. Yeah. So, but still, we are keeping our enthusiasm, and then in particular, Europe is really strong. So, so that's a good point about LightBird. So both the LightBird and CMBS4 are facing some challenges this year, but hope that both will overcome that.
Any other questions? Okay, something.
Could you give us show summary about the difference between LightBird and simultaneously?
Okay. The aperture is rather different. I mean, if you include the SO lat, that has really large aperture. So that means you can have extended coverage to of even 5,000 or so. So these blue points are SO. The LightBird red point, as you can see, this SO point stop around 40 or so. You cannot really touch on the lowest level, where we have this reionization bound, very important one for inflation science. So together with both, we hope to see the entire thing. So the basic difference is the L coverage.
This basic kind of scientific purpose.
Both are, I mean, designs are really driven by this primordial B modes. But of course, it's all that is the continuation of ACT and SPT. So it's all that is kind of a super ACT or super SPT. So that's why it can cover the broad range of science. And then if you want to launch 6-meter aperture telescope in space, it's really probably more expensive than JWST or something like that.
What's the observation band different?
Well, observation band difference, that's a good question. It's LightBird has 15 bands between 40 to 400. So it has an extension. It's all up to 280. So LightBird has higher frequency, yes. And the more bands, 15 bands.
So I'm only has
Six bands, yes.
Any more questions? Online question?
Sure, please go.
Thank you so much for a nice talk. I have a nice question. I remember at the beginning you mentioned there is the foreground contribution coming from dust. And later you also mentioned the measurement by bicep. So sorry, I forgot. Japanese detector turned out to be a kind of just detecting signal from dust. Am I correct?
Oh, it's
So
a bicep.
you mentioned two dust components, and I want to understand what's the difference between them. Maybe my misunderstanding. Maybe.
Well, the two major component. One is a dust
Yes.
component, which is on the higher frequency, and another is a synchrotron radiation, which is for the lower frequency. I don't have the. Well, this is in L, and then today I don't have this plot in frequency plot, but if you have multi bands, this spectrum in the frequency are different. There are difference between CMB, synchrotron, and dust. So by having multi bands, you can separate to some extent between CMB and the foregrounds. So that's what we are doing. And then, but it's not a simple business because the dust components and synchrotron components have some morphology and then spatial variations. So in case of light-period foreground studies, we ended up introducing more than 6,000 parameters to describe spatial variations. If you look at the tiny region of the sky, you can come up with rather simple model, gray body plus some power law, but then that varies spatially. So because of that, we gotta introduce many parameters. That's what we are demonstrating. And then another point that astronomers ask is that do you really understand the foregrounds and then physics of foregrounds? The answer is no. There are a lot of mysteries in, for example, the magnetic fields. And then that itself is a very intriguing science. But here the program is to somehow establish the foreground separation technique so that you can have adequate separation even if you don't know the physics of foregrounds very well. So we don't really introduce physical models of dust or synchrotron in our component of foreground separations. That's what we are doing. And then then that's at the end of the day, in the long future, I really hope that we have better understanding of the, for instance, the magnetic field, and then our
Hazumi-san.
program separation is sorry.
Thank you so much. I'm not actually doubting about the separation. My question is rather naive. So here you show dust component as a foreground contribution, and then can you go to the detection slide?
Detection.
Yeah.
Which one?
Maybe just a moment.
Which page?
Yeah, this one. Yeah, this one. And you mentioned this bicep 2 detection wasn't the detection of the B mode, rather detecting kind of dust contribution. So when you say this, is this dust the same dust as you mentioned in the previous slide? That's my question.
Oh yeah, this was correct. Yes, this was due to the dust. Yes.
Oh, okay. Thank you so much. I saw two dust are different dust, so I was a little bit confused.
Oh, okay.
Oh, thank you so much.
Yeah.
Then after removing this, so basically they didn't consider this dust component before pointed out by.
This was bicep 150 gigahertz only, and this is BKP. P is Planck, and Planck high frequency 353 was used to remove dust, and then we got this. Yes.
Oh, thank you so much, and I got it.
Okay, any other questions? So can I ask a prospect for Nobel Prize? So Simon's observatory, I saw that it's going to measure 0.03.
Yes.
So if the signal is above 0.03, Simon's observatory is going to get Nobel Prize. And if it's below 0.03, it's going to go light good. Is that a simple way to?
Yeah, well, besides who gets Nobel Prize, I mean, I don't know, because as you know, Higgs discovery and then Higgs got the Nobel Prize, not Atlas people, CMS people, right? If R is large and SO finds evidence first, the impact is of course huge. But I'm pretty sure that it gives a lot of discussion, and not sure if people are really convinced, because you're talking about the difference between the lensing B mode in the primordial around here. And even if you understand, you have a good understanding in lensing B mode, still people want to confirm that with the reionization bump.
So it has to be light work.
Yes, right. So the JAXA's attitude is that if we do see some hints on ground first, JAXA will be extremely happy because that gives us clear target, and then almost a guaranteed success. If I exaggerate that, yeah. So that's that can be a win-win. But the first hint, of course, will be regarded as a biggest impact result. Yeah. So in that sense, you're besides to get a Nobel Prize, the biggest impact is probably the first evidence. Yeah.
How about this bicep and cake array? How you said there was a budget cut, but then how low can they go?
Yeah, good question. I don't have a plot, but they claim similar sensitivity to SO. So we will see. Sorry, I lost ISO sensitivity. Oh yeah, here. So currently is a 0.03, and then they have a plan to get down to 0.01 and even below. And then SO claimed 0.003, and but depending on their budget and yeah, because NSF said no to CMBS4, but existing program is kept alive. Yeah, so I think
they can continue.
Yeah, to some extent. I haven't really been following the latest progress, but I think they will, in the near future, they will have an update. Yeah, we'll see.
Okay.
Yes.
It's a very exciting field. Any last question? Okay, if you have further question, you can just come to Hazumi-san after the talk and then ask. But okay, it's time to close, so let's thank Hazumi-san first.
Thank you very much.
Thank you so much.
Okay.